week. Today we are going to see the subject that is MEMS, that is micro electromechanical system. So briefly today we are going to see the introduction of or overview of micro electromechanical system. So MEMS stands for micro electromechanical system. So what is meant by micro electromechanical system? So MEMS technology consists of microelectronic elements, that is actuators, sensors and mechanical structures. So that all things are built onto a substrate which is usually silicon. So whenever they fabricate on one substrate, there are micro fabrication techniques are used. So under that micro fabrication techniques, deposition, patterning and etching, these are the micro fabrication techniques are used. So most of the common forms of that the MEMS are nothing but the bulk micro machining or surface micro machining. Then what is that the benefit of this MEMS or that the small scale integration? So huge number of that devices we can build on a single chip. So that is the main important that the benefit of this MEMS. So MEMS stands for the micro electromechanical system. So which consists of actuators, sensors and mechanical structures which is built on a single substrate. So for our today's session, the outline is first we are going to see what are MEMS, then which components are used for the MEMS, then fabrication process, then how the MEMS operate and the applications as well as that the summary and which key concept that student have to remember. So that is nothing but our today's session outline. So what are MEMS? So already we discussed that the definition or that the long form of the MEMS is micro electromechanical system. So it is the integration of mechanical elements, sensors, actuators and electronics on a common silicon substrate through the microfabrication techniques. So here some of the examples we can see. So here MEMS micro pump is shown, then MEMS micro gear in this figure is shown. So MEMS that the fluid channel we can also generate. Then MEMS micro mirror device is also here shown, as well as the MEMS headset also you can see here. So lots of things that we can fabricate by using that the MEMS technology. Then what are MEMS? So that MEMS are made up of the components which is between the 1 to 100 micrometers in size. So they are very lightweight. Then and it is in a micro. So the length for that the components is between that the 1 to 100 micrometers in size. Then device that is vary from below 1 micron to the several mm. So what is the function of that? The means functional elements of the MEMS are miniatured structures, sensors, actuators and microelectronics. So these all other combination makes that the MEMS system. Then one main criteria for the MEMS is that there are at least some elements that have mechanical functionality whether or not they can move. So that is that the main criteria for the MEMS. Then whenever we are going to think related to the scaling, because we know that micro means that the 1 to 100 means in previous slide we have seen 1 to 100 micrometer size is there. So in that cell we have to put all the technology over and then we can build that the new technology. So here scaling is very important one. So which are the scaling laws are used for the microfabrications that we are going to see. So see here scaling there is a value guide to what may work and what may not work when we start to design the world of micro. Okay, so means scaling is most important one whenever we are going to design that the microsystems. So there are two types of scaling laws. The first type is depends on the size of physical object, and second type is the involves both size as well as that the material properties of the system. So here, just like that, the two laws, the scaling in geometry we have to consider when we design that the word of micro. So surface and volume are two physical quantities that are frequently involved in micro device design. So whenever we are going to think related to the surface, so surface is related to pressure and a buoyant force in fluid mechanics. So as well as heat absorption or dissipation by a solid in convenient heat transfer. So surface is related to the pressure and force. Then volume. So volume is related to the mass and weight of device. So which are related to both mechanical and thermal inertia. So while we are going to design the micro world, the scaling geometry is very important, and whenever we are considering the scaling geometry, the surface and volume is most of that the physical quantities we have to take into the consideration. So while when we are taking into the consideration that the surface it is related to the pressure and force, and for the volume it is mass and weight. Then after the scaling, the components. So which components are used in a MEMS? So first is the microelectronics. So microelectronics plays very important role in a MEMS. So that is brain that receives and process and make a decision. Okay, and data comes from that the microsensors. Okay, so the main heart of the system is nothing but that the process receive as well as the process as well as take the action related to that. So microsensors plays the role as a receiver. So constantly gather the information from the outer surrounding that done by the microsensor. Then pass data to microelectronics for the processing. Then can monitor mechanical, thermal, biological, chemical readings, whatever the received by that the microsensor. Then next is the micro actuator. So it acts as a trigger to active external device. Microelectronics will tell micro actuator to active device. So whatever the decision is given by that the uh, microelectronics system, that given to the micro actuators, and it will be active that the device. Then the next is the microstructures. So extremely small structures built on a surface of chip and built right into silicon or the MEMS. So these are the main components of the MEMS: microelectronics, microactuators, microsensors, and microstructures. So microelectronics is nothing but the which take the decision as whatever the data received from that the microsensor, and that processed here, and it will shift means that output of that the process is given to the microactuators, and according to that that microactuator is active, means which device we want to active. And on a these all things are built on that the microstructure. So whenever we are going to design that the main system, so all the things we have to put into the 1 to 100 micrometers. So in that power system also we have to build in that much small size, because that will help to run that the whatever that the process is required for this all components. Then next comes that the fabrication process. So in this session we are not going to detail that the fabrication process, but we have to take overview on that the fabrication process. So there is a two type of that the depositions for that the fabrication process: physical deposition or chemical deposition. Again, in a physical deposition there are two types: evaporation and sputtering. And in a chemical deposition, chemical vapor deposition, atomic layer deposition. So in deposition, that the deposition deposit the thin film of material that forms like the mask. So anywhere between the few to that nanometer to the 100 micrometer onto substrate. Then physical, that material placed onto substrate. Then technical techniques include the sputtering and evaporation. In a chemical, stream of source of gas reacts on the substrate to grow product. So techniques include chemical vapor deposition and atomic layer deposition. Then substrate. So which type of the substrate we have to take? See, either silicon, glass or quartz. Then which are the thin films are for the MEMS system? Polysilicon, silicon dioxide, then silicon nitride, metals, polymers. Then after that the deposition, so we have to next stage is nothing but patterning. So transfer of pattern into material after deposition in order to prepare for etching. So etching means we have to remove the unwanted things from that the pattern. Then techniques include some type of the lithography, means for the patterning. Lithography, photography is the common one for the patterning. Then etching is also one of the important that the step of process. So that there are two types again, wet etching and dry etching. Then in a wet etching, dipping substrate into chemical solution that selectively removes the material. Process provides good selectivity, etching rate of the target material higher than that the mask material. Then and then only we will get the good results. Then in a dry etching, material is sputtered or dissolved from substrate with plasma or glass variations. So here wet etching means directly dipped into the chemical, and here we are going to dissolve that the plasma or the gas variations. So in this method, desired shapes or each depth and uniformity of the surface roughness, process compatibility, safety, cost, availability, environmental impact, all we have to take into the consideration, and according to that we have to choose either wet etching or dry etching. Then fabrication process or methods we have to see. So in fabrication methods, again there are two types. One is the bulk micromachining and surface micromachining. So first upon we are going to see the bulk micromachining. So this is that the oldest method of the micromachining technique. So it involves that the relative selectively removal of substrate to produce mechanical components. So here completed by the physical or chemical process, with chemical being used for more for MEMS production. So chemical wet etching is popular because of high etch rate and selectivity as compared to the dry etching. Then isotropic wet etching. So here isotropic means what? Each rate not dependent on the crystallography orientation of the substrate, and etching moves at equal rates in all directions. So that is isotropic. Anisotropic wet etching, each rate is dependent on the crystallography orientation or substrate. That is anisotropic wet etching. Then in a surface micromachining, process start with the deposition of thin film that acts as a temporary mechanical layer. So that is also known as the sacrificial layer. So device layer are constructed on the top, then deposition and patterning of the structure layer, and then removal of the temporary layer to allow movement of structural layer. So what are the benefits of this? So variety of structures we can form. So sacrificial and etched combinations we can use for the single-sided vapor processing. So it also allow higher integration density and lower resultant as per die cost compared to the bulk micromachining. So what are the disadvantages of this fabrication method? So mechanical properties of most thin films are usually unknown, and reproducibility of their mechanical properties is also we have to do when we are going to fabricate with bulk or surface micromachining. So here Now, bulk micromachining is shown. Isotropic etching as well as the anisotropic etching is shown here. And in a surface micromachining, sacrificial layer, then we can form the structure layer, and from that the microstructure is formed on that the substrate. So these two things are shown here. Then here that the techniques which are used for the fabrication process is shown. So this is the sacrificial material and this is the substrate. So one pattern of photoresistive material we have to press here. Then after first etching, there is a removal of this. Okay, so only this pattern of photoresistor area is remaining here, and after that again the we can add the another material layer. So again whatever pattern we want, then pattern of photoresistor material we have to place here. Then after that we have to etch in a second etching that will removed, and then completed micromachining profile looks like this. So this is nothing but that the microstructure is formed after the this fabrication process. So any type of the structure we can form by using surface micromachining. Then next is the wafer bonding. So in this wafer bonding means joining two or more wafers together to create a wafer stack. So here that shown. So three types of wafer bonding is there: direct bonding, anodic bonding, as well as the intermediate layer bonding. Then this all requires the substrate that are flat, smooth, and clean in order to be efficient and successful of the joining of the two or more wafers. So here, high aspect ratio of fabrication silicon is used. So deep reactive ion etching is used. Enables very high aspect ratio etches to be performed into silicon substrate. Then side walls of the etched holes are nearly vertical. So depth of the etch can be hundreds or even thousands of microns into the silicon substrate. So here silicon, then polymers, deposit polymers is shown, and that the whatever the deep reactive ion etching that process is shown here. Then now we have discussed related to that the what is MEMS. So which of that the scaling are required, then which type of the fabrication process are used in that MEMS system. So again there is lots of trade-offs between that the when we are going to make that the things perfectly in a electronic sector. So let us see that the which are the benefits and trade-off. So benefits, we can say it is much smaller area will require, then cheaper than the alternative. Then in medical market, that means disposable it is, and can integrate with electronics system on one chip. Then when we think about the speed, so that is the trade-off for that the speed, lower thermal time constant and rapid response time, that is the high frequency. And the for power consumption, the low actuation energy, then low heating power. Means when we are designing that the micro devices, so power, then cost, and then the speed. So these three main important points we have to take into the consideration, and we have to apply that the design theory on that the material. So maybe in that imperfect fabrication techniques are, and it is in a micro scaling, so it is difficult to design on that again the micro scales. So these are the benefits and trade-offs of our MEMS. Then let us look where these MEMS are used. So in our smartphones as well as in a tablets, cameras, gaming devices, and many other electronics have MEMS technology inside of them. So you can see here antenna switchgear module, then trans receiver is here, receiver is here, low power FPGA, that is field programming gate array, is also MEMS developed under the MEMS technique. Then sensor hub is here. Then gyro accelerometers are here. Then audio codec, that is used for the camera system, that is also here. Then tuner, that is a radio frequency tuner and demodulator is also here. Then controller, then biosensor pulses are here. Then advanced voice processor is also there. Then transmitter is also there. Then power management system we have to place here. So these many things we are handled day to day life. So we don't know about that the means, but in all these type of the applications or these type of the portable devices, so we can use that the MEMS technology inside that. So smartphones, tablets, cameras, gaming devices, and many more systems are there. So inside that we are going to use that the MEMS technology. Then MEMS operation is most of the based on that the components. So already we have seen that the components that the microelectronics, then micro sensors, then micro actuators are there. So sensor and actuators are the most of that the important components of that the MEMS system. So there are again three main types of transducers. So transducer is nothing but the convert one type of the energy into another type of the energy. So here capacitive transducers are also used. So according to that the variation between that the gap of that the plates of the capacitive, that the signal is going to be vary at the output side. So here that the capacitance effect is shown in this diagram. Then piezoelectric. Then piezoelectric also already we have seen that piezoelectric force is converted into the mechanical energy. So or that mechanical energy, that is force, is converted into the voltage. Then thermally, if the temperature increases or decreases, according to that the sensor will work. And additionally the microfluidic the material is also used. Then inertial sensors. So MEMS accelerometer is shown here, capacitor plates, then mass and the springs. And MEMS gyroscope is also one of the most important that the component while when we are going to judge the variation due to the angular velocity. So for that MEMS gyroscopes are very important one. While when the suppose for example the aeroplane this take off and that the landing, that the whatever that the angular movement of that the front side wheel that is judged by that the MEMS gyroscope. Then there are lots of application in biomedical areas also. So usually that the pressure sensors are in a biomedical application. So your blood pressure sensor on the head of a pin that is designed here. So means how much that the micrometer that the design is done here. So that we can't imagine that. So on that the head of the pin we have implemented here blood pressure. So interaxial pressure sensors are there, S marker applications are there, implemented coronary pressure measurements are there, intraocular pressure monitors are there, then cerebrospinal flood pressure sensors are there, endoscope pressure sensors are there, infusion pump sensors are there. Also retinal prosthesis is also there. Glucose monitoring and insulin delivery through that the biosensors or we can there. Then MEMS tweezers and surgical tools are there. Also cell, antibody, DNA, RNA, enzyme measurements devices or also uh, manufactured by that the MEMS technology. Then suppose day to day life we are using the car. So in the car also there are many things are fabricated under that the MEMS technology. So this is one of the example where lots of that's points are made up of from that the MEMS technology. So if you see the fuel pressure sensor, then here inertial navigation sensor, that is accelerator or rate. So air conditioning compressor sensor is also here. So manifold air pressure sensor is also, mass airflow sensor is also, force sensors where which is used for the brake and throttle pieces. Then accelerometer for that the suspension control. Then pressure and inertial sensors for the braking control. Then if you see the tire pressure sensors are also available. Exhaust gas sensor is also there. Suppose any accidental the crash will happen, then that sensor is also here. Then fuel tank for that level and the vapor pressure, that also the fuel sensor is also air backside impact sensors are there, so that automatically airbags are open inside that the car. Then micro machined accelerometer for the airbag inside also. So microphone for the noise cancellation is also. So means lots of things are manufactured by using the MEMS technology. Then again there are additional applications of MEMS. So optical MEMS are there. Then radio frequency MEMS are there. So for example, optical switches, digital micrometer devices, bistable mirrors, laser scanners, optical shutters, and a dynamic micromirror display. So if you see here, then mirror, supporter, slider, things. These also are nothing but that the optical MEMS. Then next is that the radio frequency MEMS. So it is smaller, cheaper, better way to manipulate that the radio frequency signals. Reliability is issue, but getting there. So if you see that the clamped beam resonator is here. So uh, as we see in the biomedical application, like that the optical MEMS applications as well as that the radio frequency applications are there. So summary, that is what we have learned in this session. So micro electromechanical systems are 1 to 100 micrometer device that converts electrical energy to the mechanical energy and vice versa. So micro electromechanical system name itself indicates that it will convert that electrical energy into mechanical energy or mechanical energy into the electrical energy. Then there are three basic steps of the fabrication that already we have seen, but deposition, patterning, and etching. These are the three basic steps involved in a MEMS fabrication. So again, next is that due to their small in size, they can exhibit certain characteristics that their micro equivalents can't. So MEMS produce benefits in speed, complexity, power consumption, device area, and system integration. So IC that are made up of the under this fabrication process. So IC, that is integrated circuits, is also nothing but the part of that the MEMS fabrication systems. So these benefits makes MEMS a great choice for a device in numerous fields. So there are lots of benefits of that the MEMS. Due to that, it will take that the means a great choice for the device in as compared to the other fields. Then what are the five key concepts? So student must have to remember. So that is MEMS are made up of the microelectronics, microactuators, microsensors, and microstructures. So these are nothing but the components of the MEMS. Then three basic steps of fabrications, that is deposition, patterning, and etching. Then chemical wet etching is popular because high etch rate and selectivity. Then there are three types of MEMS transducers: capacitive, thermal, and piezoelectric. Then the benefits of MEMS using that are in a speed, power consumption, size, and system integration, that is on all one in a single chip. So these are the five key concepts of that the MEMS that you have to keep into the mind. So throughout the session, these five important points we have learned today. Thank you.